So the aim of the talk is to highlight the evolution of the ARM CPU capabilities that can be exploited within the HPC concept. We're looking at the benefits of the Neon SIMD and the extensions of SVE. But we also have a trade-off in waiting for new CPU production cycles versus potentially putting accelerators in or GPU cards, for example. So what may happen is we end up rotating between various sort of silicon vendors rather than being able to establish a long-term scenario with one particular silicon vendor, simply because the way that the ARM ISA develops. Okay, so if we go to, sorry, go back one, please. So in my welcome to you, I'd like to say that the ARM ISA is definitely a first-class citizen with respect to the HPC environment. We started out sort of a few years ago now with the Mont Blanc project, which was initially a system on chip and the Mali GPU configurations. Then there was the Cavium Thunder X1 scenario, and followed by the Thunder X2. And we're looking for updates with the NVIDIA support, where we can have ARM-based servers with NVIDIA GPUs. So it's not our first rodeo. We can say that sort of ARM as a ISA benefits in the HPC community primarily on efficiency, as ARM is most noted for. And if you'd like to take a look at where we are, then there are several links here. And the last one being the ARM developer site, where you can see the various HPC concepts. Okay, next slide. So let's just review. I know I may be talking to a grandma to suck eggs, but it's always good to have a review of what HPC actually is. So we're looking for common components, and typically they're looking to be near identical configuration, so it eases scalability. A method of interconnecting the nodes, some sort of job scheduler, such as a Slurm workload manager or Univer Grid Engine. And there's ways to parallelize across multiple nodes. So it doesn't have to be literally a job scheduler, just some form of parallelization. So if we just say a bit of CPU, a bit of RAM, a bit of interconnection, a bit of storage, is that enough to really call it HPC? So if we go to the next slide. So first of all, we look at the CPU. So it's we have to break it down as to how relevant it is to a HPC environment. So we look at the number of nodes, so that's the number of chassis that we're likely to be putting together, the number of cores within those CPUs, how many threads could actually be maintained by a single CPU. Is non-uniform memory architecture supported? So can we have multiple CPUs accessing slightly different parts of the memory, but fundamentally working all towards the same goal? And whether those machines are cache coherent. So are we in sync between each of the cores with the data that is being processed? So these are elements which you don't necessarily find at the edge devices. And so what, unfortunately, HPC requires a lot of money. It's a significant investment. It's not something that a $50 system on chip edge device is really capable of. And so we're looking at the way that we scale. So first of all, the scaling of levels of cache. So within the ARM ISA, we have the macro op cache. which is just collecting a few small instructions together and then running them as a simple macro. And then level 1, level 2, level 3, as we saw on the slides, as for each core, for cluster of cores, and for the cluster of the CPUs. So what we're actually looking at is how fast can we get the data being processed. And if we've got to do multiple operations on the same pieces of data, we don't want to keep passing it backwards and forwards to, between memory. It just needs to be held within the CPU area for processing. Okay, so next slide. So where did we start? And so I referred back to the Mont Blanc and then Thunder X1 and X2. So these are based on the ARM ISA, so the instruction set architecture. The ISA doesn't stipulate how the silicon is actually laid down. You can either take a reference design or build your own IP as to how the silicon is laid out, and you implement the ARM ISA. So the first version of the 64-bit was the ARM v8, which introduced the advanced Neon SIMD architecture. So that had 32 registers of 128 bits. And that was implemented in silicon by the Ampere EMAG, the Cavium Thunder X, and the Qualcomm Cryo. When we go to the ARM v8-1, this is where we get the Thunder X2. So this is where we start to see supercomputers you've probably heard of. So the Astra supercomputer at Sandia National Labs, and the Isambard supercomputer at run by University of Bristol, alongside the meteorological office of the UK, or the Met Office in short. But ARM v8-1 is actually quite an old ISA. It's a few years old now. And in subsequent releases, we've seen 8.2 and 8.3. And what we see is there's a delay between the benefits of the new ISA and it being implemented in silicon. So we're just seeing early deliveries of the A64FX from Fujitsu with the 8.2 ISA, but specifically the A64FX has the SVE extension. Now we use potentially use SVE for larger SIMD functions. SIMD, hopefully not preaching to everybody, but single instruction, multiple data. So if you want to carry out a particular mathematical operation on a set of data, you can do it with the standard Neon of 128 bits of data, but with SVE as implemented on the A64FX, you can do it with 512 bits. So a significant improvement, and SVE extends up to 2048 if it's implemented in silicon. Now, so the ISA, it takes time to implement, so we've already had 8.3 SIMD computes. Now, if a mathematician and you're looking into complex numbers, you want to do 90-degree rotations of complex numbers, then you will be looking at 8.3 implementation in silicon before it will be available in hardware. Of course, you can do complex number 90-degree rotation in software, but it wouldn't be accelerated until the hardware is available to do so. So we're looking at the Thunder X3 and Compang 930, which are likely to support these sort of details. Now, I'm not giving out any NDA information, though this is available freely on Wikipedia and the web for product launching. So I'm not sort of taking the thunder out of other people's announcements. But I'd say there is a delay, and surprise, surprise, if you look at where 8.4, the logical numbering would be, next slide. Surprise, you've actually got the later version of ISA in your phone if you've got an iPhone 11. So that's in the A13 Bionic chip. So currently, the supercomputers of today run architectures or ISA versions which are less than the version that you may have on your mobile phone. That doesn't mean to say that the iPhone is more powerful than a supercomputer. It's not, because there's many other components which we'll talk about regarding sort of what makes a HPC. Okay, so next slide. So if we come right up to date, so the current version is 8.6. And so we're expecting that the Neoverse N2 reference design will be used by the European Processor Initiative. And we then note that there is a bfloat16 format support in hardware. And what that means is a more efficient way of handling floating point numbers at the 16-bit level. Now, the likes of Google and Intel have announced support for this. We're still waiting for support from NVIDIA for their support of bfloat16. So there's not a huge amount of vendors at the moment at this level. So we have plenty of time to implement silicon to support bfloat16. Of course, the alternative is you don't wait for the main CPU. You could have an accelerator and plug in to your main CPU to provide those extra functions. And that's what people do. So you may have an FPGA enabled accelerator, or it could be a GPU from some other design that supports the functions you need, whilst you wait for the silicon vendors to implement the latest ISA. So these versions, 8.6 and SVE2, the enhancement to SVE, were announced last year in April, and we're looking towards the end of this year where we see sort of potential launches that support 8.6. Okay, so next slide. So this is what I was alluding to. Do we look at purely what the CPU can do? Do we look at what accelerators can do for the HPC benefit? Or do we use a combination? And technology doesn't stand still. And so we wait for different fabrication sizes, whether we're going from 10 nanometer to 7 to potentially 5 in the future, to enhance the HPC environment. And the answer is not clear cut if we're saying, does one particular ISA so outperform another particular, say, a CISC implementation? So does RISC beat CISC? Some cases, yes. Some cases, maybe not. It's really a case of implementation, benchmarking, testing. Does it fulfill the role that you actually want it to do? Okay. So next slide. So beyond the CPU and the accelerators, how do we actually connect these processors together to make them optimal? So we have options of the internal connectivity. So ARM CNM 600 supports 128 core interconnectivity. So that would be connecting with a single chassis. And then between chassis, we have the options of PCIe or C6. Maybe we'll see support for CXL, so the alternative to C6. And then more proprietary connectivity, such as Aries and Tofu. So Aries from the likes of Cray, Tofu from Fujitsu. And then when we're looking at interlinking lots of chassis, then we have the network options of InfiniBand, which is low latency interconnect, and Ethernet. But the point is, again, you wouldn't get these methods of interconnects on, say, the iPhone 11. So the iPhone 11 may have the 8.4 solution, ISA, but the 8.2 solutions with these interconnects will outperform easily the mobile phone options. Okay, so if we go next slide.
Okay, Paul, just so you're aware, you've got 3-4 more minutes. You'll probably have to start wrapping up soon.
No problem. Okay, so the alternative is we go FPGA in the accelerations, and here's an example from Xilinx, which matches a Cortex A72 core with the possibility to add FPGA solutions. It supports C6 and CXL, it's got Ethernet, but the A72, just going back to the ISA architecture, is actually version 8.0. So you would have to implement in FPGA your any extended commands. Next slide. And then for HPC, we require resilience, such as error correcting code memory, dual power supplies as the basics, and core fault sensing to see if multi-core CPUs actually fail. And then I put the word containers, because containers is actually quite novel. If we just go to the next slide. Containers now give us the options that we're spending all this money on interconnects, expensive interconnects, expensive RAM, and I've been alluding to that HPC is far, far better than your system on chips. But containers give us the opportunity, if you want to consider them as throwaway services, that you could have your applications in containers running on system on chips across thousands of system on chips. And if one fails, you just restart another container on another solution. And the potential of this is such that you can scale containers from the low-end system on chip all the way through to Fugaku, to the A64FX supercomputer. If you saw the keynote earlier this morning, then there was mention on the HPC/AI using containers within the HPC environment, which is quite interesting because it allows for total scalability. Okay, next slide. Just quickly, just a reminder, we do need storage. I'll try to wrap it up a little quicker. We're looking at distributed storage of Ceph and parallel file systems such as Lustre. These are projects that we're very interested in and working on because at the end of the day, you still need to store your data somewhere. Next slide. But what applications do we run on the HPC? So there's already 292 libraries and applications that have been tested for AArch64. They're available to view on ARM's website. You could run weather prediction models, but of course the latest algorithm suggests that you can run it on PC-powered devices. In the weather prediction, there's a link there for a novel algorithm. And then we have molecular dynamics. So we're talking about COVID-19 potentially being looked at on using GROMACS. So molecular dynamic application. And then of course we have AI as a potential application for HPC. Next slide. But we're now working from home. All things are in the cloud, apart from latency sensitive edge computing devices. And we need to scale on demand, which suggests that HPCs accessed across the cloud eventually potentially form serverless computing environments. And if we look at the number of chassis sold in servers worldwide, there was an 11% drop last year in chassis sales. And of course, with the COVID-19, we're looking at market falls of 20%. So we are looking at different ways of how to make HPC pricing efficient. And the next slide. So I'll just skip over the next two slides, which are just a promotion of Linaro's Data Center and Cloud Group, which I'm the director, and the High Performance SIG Group, where we actually focus specifically on the applications which are relevant to HPC. But to conclude, the last slide, functions as a service. This is what we're actually aiming for, because at the end of the day, if everything is cloud connected, whilst as engineers in the background, we will need to know the ISA formats, the GCC compiler versions, the service consumer, the people at the end that actually use it, they just want to send a request and get an answer. They effectively become CPU, GPU, ISA agnostic. So our challenge is, if the equipment is being billed as a per use, our challenge is to ensure that the AArch64 solution match the significant number of requests. So in conclusion, HPC is moving to the cloud. Everybody's going to be wanting to use it, but they don't necessarily need the technical skills to support the infrastructure. Instead, they're looking at function as a service, fire the request, get the answer. This is the direction that I believe that we are going. Okay, and thank you.